In organic reactions, we often have polar reactions, and in polar reactions, we usually can identify an electrophile and a nucleophile. So everything can be boiled down to, except for free radical reactions, everything can be boiled down into negative being attracted to positive and positive being attracted to negative. And so polar bonds have positives and negatives in them, and then we have ionic things sometimes. It's helpful to be able to identify how the reaction is proceeding by identifying the attractiveness of a substance, and we call that an electrophile for something that's attracted to negative or electrons, and nucleophiles for things that are attracted to nuclei or positive charge. So electrophiles usually have a positive charge but can be neutral. Nucleophiles often have a negative charge but can be neutral. What do you see with electrophiles? It's going to be something that can accept a non-bonding pair or a negative charge. What are nucleophiles? Is something that has a non-bonding pair and it can give up the electrons to something to form a bond. When we have a polar bond, of course we're going to have a dipole in them, and you've already learned how to assign them by looking at electronegativities. When we go and we look at reactivity, we often will focus on functional groups. So keep this in mind. The oxygens almost always have del negatives. Nitrogens usually have del negatives. Halogens are considered to have a del negative. And metals, of course, are always going to be lower electronegativity than carbon, so they have a del positive. And if you keep these polarities in mind, it will help you think about, oh, well, I have an electrophile. Which end of this bond will it be attracted to? Well, of course, it's going to be attracted to the positive end. Okay. So electrophiles are going to be attracted to the del negative of bond dipoles, and nucleophiles are going to be attracted to the del positive. And we'll see that in a lot of reactions in the future. So you assign bond dipoles to bonds, and then you look for the nucleophiles. Where are they going to be attracted? To the carbon. If you have electrophiles, where are they going to be attracted to? They're going to be attracted to oxygen and nitrogen. Fluorine and chlorine usually don't attract electrophiles. We're going to see it's usually the oxygen and the nitrogen do, because they have non-bonding pairs that hold a lot of negative charge in them. They're compact. Fluorine can only have one bond, so its non-bonding pair doesn't tend to be available to attract electrophiles, because for fluorine to have an electrophile attached to it, it would have to have two bonds, and we don't usually see that with fluorine or chlorine. However, oxygen and nitrogen often can form, for oxygen, a third bond, and for nitrogen, a fourth bond through the non-bonding pair. And so we see them having electrophiles being attracted to them. All right, an electrophile is a Lewis acid. It's got an empty orbital, or a place where it can pull electrons into itself. Okay, so an electrophile is attracted to a non-bonding pair. Boron and aluminum, or if you find an atom that has a positive or a del positive, can all attract an electrophile. A nucleophile has a non-bonding pair, and so it is a Lewis base. Okay, they can donate their electrons to boron and aluminum since they have empty orbitals, and carbons with a positive charge can take a nucleophile. They have an empty orbital on them. And even carbons with a del positive can accept a nucleophile if they give up one of their bonds. And we'll go look and see that. So a nucleophile always has a non-bonding pair, or it can have a pi bond, which it's giving up its electrons to act as a Lewis base. Remember to always draw the arrow so it goes from the nucleophile to an electrophile, because we're showing electron movement, not atom movement. There are some bonds that we draw with a del positive and del negative, even though the electronegativity values don't indicate that they should. And the reason why is that large atoms like sulfur and iodine, which are not of lower electronegativity than carbon, they're huge atoms, so that when a negative charge comes close to this del positive or to a carbon, the electrons push away onto the sulfur so as to form a del positive. So the carbon in a carbon-sulfur bond acts as if it has a del positive on it. Likewise, a carbon in a carbon-iodine bond acts like there's a del positive there because of the polarizability of that bond and the ability of a nucleophile to push electrons onto the iodine or sulfur as it approaches a carbon. Here are some nucleophiles. Notice some of the nucleophiles have negative charge, some have no negative charge. What do they all have? Non-bonding pairs. Here are some electrophiles. The hydrogen in a hydronium ion is electrophilic. Why? Because a nucleophile can be attracted to the hydrogen, not the oxygen, and pull it off of the oxygen. If I look at this bond, there is a polarity in this bond that puts del positive on the carbon. Again, a big polarizable atom here. That del positive can attract nucleophiles. This bond has a del positive on the carbon and a del negative on the oxygen, and nucleophiles are attracted to the carbon. Go ahead and try this problem. Which of these would be the least likely to serve as a nucleophile in a chemical reaction? Okay, if I look at these two have negative charges, so automatically you can recognize that they're nucleophiles. They are going to be able nucleophiles. If I look at ammonia, it has a non-bonding pair on the nitrogen, so it can serve as a nucleophile quite easily. This, the carbocation here, cannot serve as a nucleophile. What is it? It's an electrophile. Anything with a positive charge will not be attracted to a positive nucleus, so this is never going to be a nucleophile. So let's go through a reaction in which we look at how the electrons move and how we assign electrophile and nucleophile. If we look at hydrobromic acid, we can do an addition reaction of hydrobromic acid to a compound that has a double bond in it. The double bond has a pi bond in it that has high energy electrons. So those electrons can act as a nucleophile and reach out to grab the hydrogen off of hydrobromic acid. It actually is reaching out and grabbing H+, the proton, from the hydrobromic acid. Why does this act as an electrophile? Because in this bond, you have a large del positive here and a large del negative there. So we have the nucleophile here reaching out to grab the electrophile. And then, since hydrogen can only have one bond, it has to give up those electrons to jump onto the bromine. So, nucleophile, electrophile. Or we can say the pi bond is a nucleophile and the proton is the electrophile. Once the proton has been grabbed by the pi bond, the electrons that were in that pi bond are now in this bond to the proton. It leaves a positive charge behind on the carbon because the pi bond electrons reached out to grab the proton, so they left one of the carbons and it leaves a positive charge on it. The bromide is formed from the bond that was between the hydrogen and bromide jumping onto the bromine to give it a negative charge. So now this is a nucleophile and this is an electrophile. So the electrons move from the bromide to the carbocation to form the bond. So here's the entire mechanism pi bond nucleophile grabbing the proton in hydrobromic acid, the electrons in that bond jumping onto the bromine to form bromide, the bromide nucleophile grabbing the carbon with a positive charge on it and forming the bond to form a bromo compound. Notice the double bond had the hydrobromic acid added across it. Y'all see that? I assume that you will be able to do the same addition reaction on future alkenes. We'll have some problems to try. This mechanism emphasizes these rules for using the curved arrows. The electrons are always going from the nucleophile to the electrophile. Of course, it doesn't have to be negatively charged. It can just be a neutral, non-bonding pair atom. If it's negative charge, it can reach out and grab this from here. The hydrogen does not have to be charged. It can give up its electrons and form a bond. There's just a large del positive here. This actually shows this can act as a nucleophile now because there's a non-bonding pair, except there's no electrophile nearby. And this now can act as a nucleophile also, but there's no electrophile nearby for it to react with. But this is the mechanism for the protonation of this methoxide anion with an acid. Notice, overall negative charge, overall negative charge. Charge was conserved. This reaction here again shows our rules. Nucleophile, reaching out and grabbing the electrophile, and then the electrons jumping onto the oxygen. Notice this compound has a positive charge on the oxygen. Just because it has a positive charge doesn't make it an electrophile. The atom that has a positive charge must have the capability of forming a bond. This cannot form a fourth bond. So what is the electrophile? It's actually the proton that's stuck on a non-bonding pair there. Notice the nucleophile grabs the proton. These electrons then become a non-bonding pair. So it's not always the atom that has a positive charge that is the electrophile. So now here's a reaction shown, and what I want you to do is to draw the arrows that are showing how this reaction occurs. Pause it, draw in the arrows, and then restart the lecture. Okay, for this reaction to occur, what has to happen is this is the nucleophile. So the electrons are going to go from the pi bond and grab the proton. Then the electrons that are in this bond are going to jump onto the chlorine. So what happens is once the pi bond electrons grab the proton, you get a positive charge on the carbon. That positive charge then is ripe for nucleophilic attack. So here's a nucleophile that is left over from the electrons here jumping onto the chlorine. So what happens? They dive in and form a bond there. What's the product of this reaction? Okay, to do this reaction, we recognize this is an addition reaction, and when we have hydrobromic acid or hydrochloric acid and a double bond, one of the hydrogens ends up on one end of the double bond, and the halogen, or the halide, ends up on the other end of the double bond. So the product of this reaction is here, this bromocyclopentane. Notice that the hydrogen is over here. We don't write it though because we know there are two hydrogens on this carbon. There's one hydrogen on this carbon. Now there's two. So where did this hydrogen end up? Right here on this carbon. In this two-step reaction, what I want you to do is identify the nucleophile and the electrophile in each step, and then draw in the arrows for the reaction to occur. Okay, to do this reaction, we look over here at this part first, and since this carbon has a positive charge, it's pretty obvious this will be the electrophile. And since the oxygen has non-bonding pairs, it's pretty obvious this will be the nucleophile. Now, if I look at this step, in order to figure out what's the electrophile and what's the nucleophile, you just don't automatically say, because there's a positive charge there, that is the electrophile. You have to look for what's happening in the reaction. What's happening in the reaction is that the proton on this oxygen is coming off. So it's actually giving up the proton. The nucleophile here is this the water molecule, and the non-bonding pairs are reaching out and grabbing this proton, and then these electrons are jumping onto the oxygen to form a non-bonding pair. So, electrophile, nucleophile. The proton on the oxygen is the electrophile, and water is the nucleophile. The arrows for these reactions is this. First of all, the electrons on the nucleophile reach out and grab the proton, the carbocation. And then over here, the non-bonding pairs reach out and grab the proton, and the electrons jump onto the oxygen. Which of the following could be a nucleophile? Now, when we're looking at this, go ahead and pause the lecture and then restart it after you figured it out. When we're looking at these, we can see borane here, it has no non-bonding pair, so it cannot be a nucleophile. If we look at hydrochloric acid, now the hydrogen in the hydrochloric acid has a large del positive, so this would be a poor would not be a nucleophile. If the bond here were to dissociate and cause a chloride to be made, it could be a nucleophile, but they're not asking about there. They're looking at this in particular. And so, as it's written, it's not a nucleophile. If I look at this molecule, there's no way that bromine is going to form two bonds. In organic chemistry, bromine is always shown as forming one bond. So it already has a bond to the carbon, so it's not going to reach out and grab anything. The nitrogen here, though, has a non-bonding pair on it. So the nitrogen can act as a nucleophile because it can form a fourth bond on it and get a positive charge in order to be a nucleophile. In each step here, identify what is the nucleophile and what is the electrophile. Okay, in this first step, since the electrons are reaching out to grab this proton here, or the hydrogen that's in this hydrogen chloride bond, this is the nucleophile, and the electrophile is the hydrogen with the del positive on it. In this step, the carbocation is the electrophile, and the chloride is the nucleophile.